Welcome to this fascinating scientific lecture on the Digital Droplet Paradox, one of the most counterintuitive phenomena in microfluidics. Today we're going to explore a remarkable paradox. How can chaotic, unstable flow conditions produce perfectly regular, identical droplets? The phenomenon is striking. Even when feeding conditions fluctuate wildly, microfluidic droplet generators produce droplets that are essentially identical. This defies our basic intuition. We expect that if inputs are chaotic, outputs should be chaotic too. But nature has a surprise for us. Let me start with a familiar analogy. Think about a dripping faucet in your home. A chaotic faucet drips irregularly. Sometimes drops fall quickly, sometimes slowly. The timing is unpredictable due to complex fluid dynamics. Yet here's the key observation. Even though the timing is chaotic, each individual drop is remarkably similar in size and shape. Why does this happen? It's due to a fundamental instability called the Rayleigh Plateau instability. Let's understand this instability mathematically. Lord Rayleigh discovered this in the 1870s. When a liquid forms a cylindrical jet, it's unstable. Any small perturbation grows exponentially due to surface tension. The critical wavelength lambda sub c equals 2 pi r times the square root of 2, where r is the jet radius. Perturbations at this specific wavelength grow fastest and dominate the breakup process. The growth rate omega is proportional to the square root of surface tension sigma divided by density rho times radius cubed. This growth is exponential. Once it starts, the breakup happens incredibly fast, typically in milliseconds. Let's work through a concrete numerical example with water. Suppose we have a water jet with a radius of 100 micrometers. That's about the width of a human hair. In SI units, that's 10 to the negative 4 meters. The critical wavelength is 2 pi times 10 to the negative 4 times the square root of 2, which equals approximately 890 micrometers. Now here's an interesting question. What volume droplet does this produce? The volume is approximately pi r squared times lambda c. This assumes the jet breaks into droplets spaced by lambda c. Plugging in the numbers, we get about 28 nanoliters per droplet. Now let's move to the heart of our topic, the microfluidic droplet generator. In a microfluidic T-junction or flow-focusing device, two immiscible fluids meet. The dispersed phase breaks into uniform droplets in the continuous phase. The behavior is governed by two critical dimensionless numbers. First is the capillary number. Ca equals mu u over sigma, where mu is viscosity, u is velocity, and sigma is surface tension. The capillary number tells us the ratio of viscous forces to surface tension forces. Second is the Weber number. W equals ρ(h)O u squared L over sigma, where ρ(h)O is density and L is a characteristic length. The Weber number compares inertial forces to surface tension. Now we come to the central question. Why does instability produce such remarkable regularity? The answer lies in the nonlinear dynamics of the breakup process. Here's the key insight. The system has a natural selection mechanism that picks out a preferred frequency. There's a spectrum of possible perturbation wavelengths, but only one wavelength has the maximum growth rate. That's the one that wins. This is called mode selection. The fastest growing mode dominates and suppresses all others. Mathematically, omega max occurs at k equals kc, where k is the wave number and kc is the critical value. Let's look at some real-world numbers from actual microfluidic experiments. In typical microfluidic devices, here are the numbers you'll encounter. Channel widths range from 50 to 200 micrometers. Flow rates are typically 0.1 to 10 microliters per minute. Droplet generation frequencies range from 10 to 1000 Hz. That's 10 to 1000 droplets per second. The coefficient of variation in droplet size is typically less than 2%. That's remarkably uniform. Let's do a quick calculation. If we know the flow rate, can we predict the droplet size? The volumetric flow rate Q equals frequency F times volume 5 per droplet. If Q is 1 microliter per minute and F is 100 Hz, then V equals 167 picoliters per droplet. The geometry of the microfluidic device plays a crucial role in determining droplet behavior. At the constriction point or junction, the pressure builds up until it overcomes surface tension and a droplet pinches off. The constriction geometry acts like a clock that sets the droplet formation rhythm. The pressure difference delta P needed to form a droplet scales as 2 sigma over R, the Young-Laplace pressure. Each time a droplet forms, the pressure must build up to this same critical value. This creates the regularity. Why does this matter? The Digital Droplet Paradox has profound practical applications. First, digital PCR. By partitioning samples into thousands of identical droplets, we can count DNA molecules with incredible precision. Second, high-throughput drug screening. Each droplet becomes a microreactor, saving precious reagents. Third, single-cell analysis. Each cell gets its own identical droplet environment for consistent measurements. Fourth, material synthesis. We can mix reactants with exact stoichiometry in every droplet. Let's dig deeper into why surface tension is so dominant at this scale. The bond number BO equals RHO GL squared over sigma. It compares gravitational forces to surface tension. For a 100 micrometer water droplet, the bond number is approximately 0.00001. Gravity is negligible. This tiny number means surface tension completely dominates the physics. Gravity is irrelevant at this scale. Surface tension pulls equally from all directions, creating a perfectly spherical droplet. This uniformity is key to reproducibility. There's a beautiful energy principle underlying all of this. The surface energy E equals sigma times area A. For a fixed volume, a sphere has the minimum possible surface area. This is the isoperimetric inequality. The system always evolves to minimize energy. dE by dt is always negative during droplet formation. Nature automatically finds the lowest energy configuration, which is a perfect sphere. That's why droplets are so uniform. Let's examine more carefully how the frequency gets selected. Here's a question for you. What exactly sets the droplet formation frequency? Why is it so regular? The answer is a balance between the incoming flow rate and the critical volume at which a droplet must attach. The formation time T subform equals the critical volume 5 subcrit divided by the flow rate Q. Therefore, the frequency F equals 1 over T form, which equals Q over V crit. This is deterministic. The critical volume depends only on the device geometry and surface tension, both of which are fixed. Now let's address the robustness to fluctuations, which is central to our paradox. Suppose the input flow rate fluctuates by plus or minus 10% due to pump noise or pressure variations. Remarkably, the droplet size typically changes by much less than 10%. Why? There's a negative feedback mechanism. If more fluid enters, the pressure builds faster, the droplet pinches off sooner. The relative volume variation delta 5 over V scales as delta Q over Q to the power of about 0.3, not 1. This sublinear scaling is what provides the remarkable robustness we observe. Here's another powerful analogy. Think about digital electronic systems. In digital electronics, a noisy analog signal passes through a threshold device and becomes a clean digital signal. The droplet generator acts like an analog to digital converter. Continuous fluctuating flow becomes discrete identical droplets. The threshold is the critical pressure needed for droplet pinch-off. This threshold is always the same. For the advanced students, there's another important dimensionless number called the Ohnesorg number. The Ohnesorg number O equals mu over the square root of Rho sigma L. It can also be written as the square root of Weber number divided by Reynolds number. O characterizes the relative importance of viscous forces in the breakup process. When O is much less than 1, inertia dominates. When O is much greater than 1, viscosity dominates the dynamics. Researchers have mapped out stability diagrams showing different regimes of droplet formation. In capillary number versus flow rate ratio space, there are distinct regions. The dripping regime produces monodispersed droplets. In the dripping regime, droplets form right at the junction. This gives the highest uniformity. In the jetting regime, a jet extends downstream before breaking up. Uniformity is still good due to Rayleigh plateau. Of course, real systems have complications that can affect uniformity. Surfactants at the interface can alter the surface tension dynamically and affect droplet formation. Temperature changes affect both viscosity and surface tension, potentially introducing variations. Over time, channels can foul or clog, changing the effective geometry. Despite these complications, the fundamental selection mechanism remains remarkably robust. Let's step back and consider the broader implications of this paradox. Order emerging from chaos is a recurring theme throughout nature. It's not unique to droplets. We see it in crystallization, pattern formation in chemical reactions, and biological rhythms. The key ingredient is nonlinear dynamics combined with some form of mode selection or frequency logging. This teaches us that instabilities can be constructive. They can create order rather than just destroy it. How do we know all this theory is correct? Let's look at experimental validation. High-speed cameras operating at 10,000 frames per second can capture the entire droplet formation process. Measurements consistently show droplet size uniformity of 1 to 2% coefficient of variation. The droplet formation frequency is stable to better than 0.1% over thousands of droplets. These experimental results beautifully confirm our theoretical understanding. Let me summarize the key insights from this lecture. The Digital Droplet Paradox shows how fluctuating, chaotic inputs can produce perfectly uniform outputs. The mechanism is hydrodynamic instability combined with natural mode selection that picks the fastest growing wavelength. At the microscale, surface tension completely dominates, creating deterministic behavior. This enables revolutionary applications in digital PCR, drug screening, single-cell analysis, and materials synthesis. This phenomenon reveals something profound about the physical world. Nature uses instability not as a problem to be avoided, but as a tool to achieve precision and reproducibility. The same mathematical principles appear across many scales, from microfluidics to raindrops to planetary formation. Understanding the digital droplet paradox deepens our grasp of nonlinear dynamics and emergent phenomena. Thank you for joining me on this journey through one of nature's most elegant paradoxes.